In our last video lecture, we discussed permutation and combination. So in this session, we're going to apply what we have learned in permutation combination in solving some problems. Okay, but before we solve some problems, let's have a review about permutation combination. So permutation has a formula P and R is equal to n factorial divided by n minus r factorial. So n is the number of elements in a set, the population that we are talking about, and r is the number of elements or items that we're going to get from the population, from the set, wherein we're going to derive the pattern. Okay, so that's n and r. But for combination, the formula is n factorial divided by r factorial times n minus r factorial. Okay, the difference between combination and permutation is the treatment of the arrangement of R, of the different elements in a pattern. So for example, we have 1, 2 for one pattern, second pattern 2, 1. For permutation, this is considered as 2 patterns. Okay, but for combination, it is considered as 1 pattern. Okay, the 1, 2, 2, 1, since they have the same elements. Okay, so in permutation, the order of our pattern is considered in determining the pattern, while for combination, it's not. Okay, so that's the difference between permutation and combination. So now let's move on with solving problem number 1. So let's set S contains 1, 2, 3, 4, 5. And we're going to list all the 3 permutation of S, list all the 3 combination of S. So it means we're going to get 3 elements from set S and create a pattern for the permutation and for the combination. Okay, so before we list the patterns, so we get the number of patterns first that could be derived from the given set S. So let's start with permutation. 3 permutation. So it could be solved by the formula of permutation, n factorial divided by n minus r factorial, wherein n is equal to 5, r is equal to 3. So we have 5 factorial divided by 5 minus 3 factorial. The result is 60 patterns. So we have 60 patterns for 3 permutation for set S. And for 3 combination, so using the formula of combination, we have 5 factorial divided by 2 factorial times 3 factorial. So 2 factorial is from n minus r. Okay, don't forget that. 5 minus 3 is equal to 2. So I just directly substitute 2 instead of writing it 5 minus 3. Okay, and then the result of this equation is 10. So we have 10 patterns for combination, 60 patterns for permutation. Since we have lesser number of patterns for combination, I'm going to get first the patterns under combination. So 3 combination, let's get 3 elements from the given set. So let's start with the first 3 elements. We have 1, 2, 3. We have 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5. Then we have 2, 3, 4, 2, 3, 5, 2, 4, 5, and last 3, 4, 5. So just to check if we got all patterns, we're going to count it. So again, we have 10 patterns. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we already got all patterns for 3 combination. Now let's move on with 3 permutation. So to have an easier way of determining the pattern for the 3 permutation, I'm going to base our answer based on 3 combination. Okay, so again, in permutation, the order of our elements mean a different pattern. Okay, so it means if we're going to rewrite 1, 2, 3 in a different way, in different arrangement, we could derive a new pattern. Okay, so for example, 1, 2, 3 could be rewritten as 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Different order means different pattern for permutation. So we have 6 patterns from 1, 2, 3. Okay, since we have 10 patterns for combination, it means we have 6 for each combination pattern. So we have 6 times 10, we have 60, which is equivalent to our solution earlier. Okay, so these are all the patterns derived from set S with 3 elements permutation. Okay, and also problem number 1 shows the difference between combination and permutation. Okay, now let's move on with problem number 2. So this involves combination. This is actually a combination problem. Okay, so how many bits string of rank 12 contain exactly 3 ones, at most 3 ones, at least 3 ones, an equal number of 0 and 1s? So we're going to count the number of 0 and 1, combination of 0 and 1 that will yield the criteria. Okay, so this is combination. Okay, so let's start with letter A. Exactly 3 of 1s. So in the 12 bits, there should only 3 of 1s. No more, no less. Okay, it means 3 of 1s and 9 of 0s. The location of 1 could be from the start bit, end bit, middle bit. Okay, we don't care as long as we have 3 of 1s. So using combination formula, so we have this solution. So from 12 elements, we're going to get 3. We're going to consider 3 elements, which is 3 of 1s. So that's how we are going to solve it. So 12 factorial divided by 3 factorial times 12 minus 3 factorial. And then the result is 220. So it means we have 220 patterns for exactly 3 of 1s. Okay. Now let's move on with at most 3 of 1s. So it means the number of 1s doesn't exceed 3. Okay, at most is 3. So we could have 2 of 1s, 1 of 1s, or it is not existing. Okay, so since based on what I have stated, we have different scenario. For each scenario, we're going to get a combination, okay, pattern. So 1 for 0 of 1s, 1 of 1s, 2 of 1s, and 3 of 1s. So we have 4 solution, 4 combinations that we're going to get. Then afterwards, after getting the patterns, number of patterns, add those 4 patterns to get the total patterns that would represent at most 3 of 1s. Okay, so let's start with none at all. No one's in our pattern. So that walang 1. So this will be the solution. Okay, if we're going to use the combination formula. But if we're just going to inspect the pattern, so definitely we're going to have 1 pattern lang, because we only have zeros in our 12 bits. You cannot change the value to 1 since it doesn't follow non-existing of 1 in our pattern. So we only have 1 pattern, lots of 12 of zeros. So that will be the first scenario. Second scenario, we have 1 in our pattern. 1 of 1s in our pattern. So C 12 at 1. So we have 12 factorial divided by 1 factorial times 12 minus 1 factorial. Result is 12. This is correct, because 1 position will be 1 and the rest will be 0. And how many positions do we have? We have 12. So 1 pattern times 12 position, so we have 12 patterns. So this is correct by just evaluating how 1 of 1s work with 12 bits. Okay, now let's move on with 2 bits at 2 of 1s in 12 bits. So this is the solution, and the result is 66. And for 3 of 1s, so we already solved it. So we have 220. So we have the 4 scenarios, and to get the total that will represent at most 3 of 1s, so just add 1, 12, 66, and 220. That will be the total. So we have 299 patterns that represent at most 3 of 1s. Okay? So now let's move on with letter C, at least 3 of 1s. So to solve this, we have two options. We're going to get all the scenario wherein it fit the scenario, at least 3. So it means all bits are 1, 11 of 1s, 10 of 1s, 9 of 1s, 8 of 1s, until up to 3 of 1s. So by counting the number scenario, we have 10 scenarios. Then we're going to add everything. That will be the total. But for me, it's so tedious. So instead, I'm going to get the excluded scenario, and I'm going to subtract it from the total pattern. That will be easier. Since the number of excluded scenario are just 3. Okay, what are the scenario which didn't, or don't um, um, meet the requirement? At least 3. Okay, minimum is 3. So it means we have 2 of 1s, 1 scenario, 1 of 1s, and 0 of 1s. So we have 3 scenario. So against, okay, then it's easier to solve 3 scenario. And then later, I'm going to subtract it to the total number of patterns. Okay, so we already solved the zeros of 1s, 1 of 1s, and 2 of 1s in our pattern. So we have 1, 12, 66. Now the problem is the number of patterns for 12 bits. So we could easily solve it using product formula, product rule ladder. So for the first position, how many patterns that could we have? 2. Second pattern, 2. Third pattern, 2, until up to 12. Position, 2. So it means 2 times 2 times 2 times 2 times 2 until the 12 bit. Okay? Or basically it's just 12 raised to 2. So the answer is 4096. So you're just going to subtract 112 and 66 to 4096. We get the number of pattern for at least 3 of 1s. So we have 4017. Okay. So now let's move on with letter D. We need to have an equal of 0 and 1s, number of equal of zeros and 1s. So it means 6 bit for 0, 6 bit for 1. So from 12 elements, we're going to get 6 as 1. So the solution will be this, and then the result is 924. Okay, so that will be problem number 2. Now let's move on with problem number 3. So it involves permutation. So how many permutation of the letters A, B, C, D, E, F, G, H contains the string ED, the string CDE, the string BA and FGH, and the string ABDE and AGH? So we already discussed this. A similar problem was discussed on our last video lecture. So if we have a group of letters, it will be considered as one element when we count it, okay, to get the population. Okay? And in case we're going to get, if we're going to use all elements, so instead of using the formula I have stated earlier, the formula that we're going to use is just n factorial, since every element will be used. Okay. Now let's answer letter A, the string ED. So how many letters is left when we remove ED? We have A, B, C, F, G, H. So we have 6. Okay. And then ED will be considered as one element. So in total, for our permutation, we have 7 elements. So it will be 7 factorial. Result is 5040 patterns. So a pattern that contains ED. Okay. Now let's move on with the string CDE. It's the same as with ED. So instead of having 2 letters in one superletter or in one group, it will be 3 letters. And the number of letters left, okay, in our set will be A, B, F, G. So we have 5 CDE. So consider as one element, total 6. So therefore, the permutation pattern is, number of permutation pattern is 6 factorial is equivalent to 720. Okay. Now let's move on with letter C. Same scenario, same treatment. So we're just going to have 2 super letters, B, A, and F, G, H. Okay, so what are the letters left for us for the permutation? So we have C, D, and E. So we have 3. And B, A, and F, G, H, we have 2 elements, super letters. Adding 3 plus 2, we have 5. So 5 factorial is 120. So we have 120 patterns that contains B, A, and F, G, H. How about A, B, D, and N, G, H? Okay, same treatment. A, B, D, E, and G, H will be considered 3 elements. Okay, and the number, the letters that is not completed in our super letter are, which are C and F. So we have 2. So 2 plus 3, 5. 5 factorial. So we have 120. Okay. So that's problem number 3. So that will be my last slide for this session. So if you have any question, kindly send me a message, please. Okay. And thank you for listening. Thank you for viewing this video lecture. See you on the next video lecture. Thank you.